Vou começar.
Okay. Well, hi everyone. Let's start the last day of the event. I remember that the talks and conference slides and videos are available on the event's website. Well, I am very happy, and it's a pleasure to introduce the next speaker, the Professor Carlos Munuera from Universidad de Valladolid in Spain. And Professor Carlos was, well, a great researcher, was a great friend of Fernando. Mm. Thank you so much, Professor Carlos, for participating in this event. Thank you. And well, the title of the talk is Algebraic Geometry Codes from Castle Corpos.
Thank you, Guilherme. Thank you for your words. And thanks to the organizers for inviting me to this meeting, which has the special meaning of being in memory of Fernando. I met Fernando years ago in Germany. And since then, we start a relation of friendship and also of scientific collaboration. We have worked together in some topics. And precisely, I think is appropriate to speak about one of these topics, which is castle curves, and codes. And of course, other colleagues have participated in its particular study. I would like to mention Alonso Sepúlveda, Wilson Olaya, Wanderson Tenorio, and others. I don't know if my talk will be looking at the audience will be too trivial for most for the audience. I don't know if you're familiar or not with error correcting codes. I would like to start from the beginning. If from the very beginning. So maybe what I will say is too trivial for. I apologize in this case. The study of codes began in the 40s, years ago. Works with Richard Hamming and Marcel Golay and others. And the purpose was to construct codes, good codes. What is a code? A linear code is of type NKD, is just a k-dimensional linear subspace of fq to the power n. And here D is the minimum weight of a non-zero code word, and weight means the number of non-zero coordinates. And what we want is to obtain good codes. Here n gives the number of symbols to be transmitted. K is the number of symbols carrying information, and D is the capacity of the code to correct errors. So good, in some sense, means to we want to optimize simultaneously the ratios D over n and K over n. Yeah. This is in principle. In practice, these numbers are not easy to compute. K is maybe linear algebra. D certainly is not. It's difficult to compute. And well, we have bounds, of course. The most important to know is the singleton. D plus K is at most n plus 1. And well, anyway, we want to make these numbers as big as possible simultaneously. How to do it? Well, the answer of coding theorists over time has been to introduce more and more mathematical structure in the codes to be able to compute parameters and to be able to make them good. And for example, to construction. This is Red Solomon codes are by far the most used in practice. They were introduced by Edwin Red and Gustav Solomon in the 70s, in the 60s, yeah. The original construction is not this one, but this way to see that this code is interesting. We consider the set of polynomials of degree at most k minus 1. We take points in the finite field, and the code is the set of evaluation of these polynomials over the alphas. The parameters are easy to compute, are these, and the code is MDS. We have equality in the singleton bound. As you see, the idea is we are injecting a property of polynomials into the code. We can generalize this idea in a simple way. We take we take the projective line or affine line, or in general, we can take a geometrical object, we can take points, and we can take functions that can be evaluated at the points. And when the evaluation is linear, then we get linear code. And we can use the properties of the geometrical object to construct, to obtain properties in the code. Of course, these codes are called evaluation codes. The most natural choice for a geometrical object is a curve. This construction leads to the algebraic geometry codes or geometric Copa codes introduced by Valery Denisovich Copa in the 70s. This is not the construction of Copa, but it follows the previous structure. We take a curve, we take points, construct the sum of all points. This is the divisor G. We take a set of functions to be evaluated. We take a Riemann-Roch space or some rational divisor, and we evaluate. Then we can use algebraic geometry to have properties about the parameters. For example, the dimension is LG minus D, where L mean the dimension of the Riemann-Roch space. And we have this expression for the minimum distance. The minimum degree of a divisor, effective divisor, is smaller than D with this dimension bigger than 0. But still, in general, it's difficult to compute, but we have bounds here. We get bounds here. For example, the minimum distance is computing is not difficult to see that this is at least n minus the degree of G plus this number, gamma A plus 1, where gamma is the gonality of the curve and A is the abundance of the code, the dimension of the kernel. Using this kind of relation, we can prove the inequalities you see here in blue. The sum K plus D is, well, is n plus 1. This is singleton, but the interesting part is the left hand inequality. This number can drop at most the genus of the curve unites from n plus 1. So when the number n is large with respect to the genus, we get good codes. Usually, when people restrict to this case, the degree of the divisor G is at least 2 times E at most n. In this case, the evaluation is injective, the kernel is 0, and we have even simpler expressions for the parameters. K is LG. Riemann-Roch says that this is the degree plus 1 minus the genus. And the minimum distance is this one. This is in general in most papers, in most works, people even restrict to this particular case when the divisor G is a multiple of a single point, a single rational point on the curve. Then the code is obviously called one point. And in this case, the properties of the code are related to the Weierstrass semigroup, the semigroup of pole orders of functions having poles only at Q. And we can simplify all computations. Note that, for example, the dimension is obtained just from the semigroup. And well, the distance is not obtained from the semigroup, but we have good bounds on the, for example, the well-known, the famous order bound and like this. But for many problems, this works well, but for many problems, this restriction is too strict. We can enlarge a little bit the family by considering isometry. Two codes are called isometric if they are related like this. One is obtained from the other by multiplying by a vector with non-zero coordinates. And the multiplication means here coordinate-wise. So we can consider not only one-point codes, but codes isometric to one point. Isometric means, in fact, this is an isometry for Hamming metric. So isometric codes have similar properties and parameters like this. In general, it's not simple to characterize when two codes are isometric, but for algebraic geometry codes, we have a good property that equivalent divisors give isometric codes. So it's not difficult in principle to have this kind of relation. An example in Hermitian codes. In some sense, these are the prototype of all HG codes. Codes over the Hermitian curve, this curve with this equation over FQ squared. It's simple to check that this line, this curve has one point at infinity, just one point, that vertical lines meet the curve at Q different points, while horizontal lines with this condition meet the curve at Q plus one different points. So in terms of divisors, we have many relations. This multiple of Q times Q is equivalent to a divisor, the vertical line, the one given by the vertical line, which is smaller than D, and the same for horizontal lines. And it follows that the curve has Q to the power 3 plus 1 point, which is maximal. The semigroup is generated by Q and Q plus 1. Well, this comes from the equation. And D is equivalent to Q to the power 3 times Q. And so we have many equivalences of divisors, and these equivalences can be used to manage with the curve, with the parameters in particular. For example, if you look at the dimension, here everything depends on Q. So the dimension can be obtained from the Weierstrass semigroup. The minimum distance, again, doesn't follow from the semigroup, but we have, again, we can apply, again, equivalences, and we have good bounds. The result is that for Hermitian codes, almost everything is known, or many things are known. The parameters are known in full, the generalized Hamming weights are known in full. This is rather unusual. Very few codes for very few codes we have this kind of properties. Another example. This is probably the most famous code, Hamming code. we are speaking about evaluation code, and this is certainly is not. This Hamming code is the null space of a matrix. The matrix having as columns the coordinates of all points in some projective space. So it is not evaluation, but it's orthogonal of an evaluation code. Orthogonal means with respect to the usual linear inner product. And this means it is interesting also to consider orthogonality. The orthogonal of a code is usually called the dual, the code. And when a code is equal to its dual, we say it is self-dual. When it is contained, it is called self-orthogonal. We shall see a little bit later the interest of this definition, these objects. In the case of AG code, the case we are interested in, the dual of one AG code is again AG code. We have this relation. This was discovered by Henry Schichten years ago. So D plus W minus G, where W means a canonical divisor of a differential form with simple poles and residue 1. So it holds that it is a G, but when the code is 1 point, the dual is not in general. And here is where isometry plays a role. It's not 1 point, but it can be isometric to 1 point. Hiram yesterday gave us a talk about the duals of evaluation codes, if you remember. In the case of Hermitian codes, what happens here? Well, we have this function, this function. We remember the divisors of vertical lines. We can compute the divisor of this differential form. This kind of divisors are well known. We get it is of this form, and the dual here is 1 point code. The dual of one Hermitian code is 1 point code, which is again rather unusual. Why for the Hermitian? Or how can we ensure this kind of properties which are good for applications? And well, the last ingredient to speak about Castle codes is the Lewis bound. We say before, Hermitian curves have many points, maximal. Since the introduction of algebraic geometry codes, a line of research is a start to find curves with many points and to find bounds. And the purpose seems to be to have good codes, to obtain good codes from them. However, if we focus, as we are doing, on AG 1 point AG codes, we see that there is a missing ingredient here in most bounds. That it's we are a height-like point, a special point which is Q, while most bounds treat all the points equally. So for this reason, this bound is especially interesting. It is introduced by Lewis in the 1990. And, well, take a curve, take a rational points, where's the semigroup, and the number of points is bounded like this: Q times the multiplicity, the first non-zero element in the semigroup, plus 1. It is interesting about this bound that it was originally proved by using the properties of algebraic function fields, while it is simple to prove it through lines using coding theory. We take a function with polar order at Q P2, the multiplicity. The evaluation of the function is the same as the evaluation to the function to the power q. So the evaluation cannot be injective when restricted to this space, q times v2q. So this number should be bigger than n, bigger or equal to n. This is just the bound. Anyway, we can define already Castle curves. We impose the two conditions. In a way, we try to have the properties that makes Hermitian curves good, capturing the properties of Hermitian curves. We have a curve with a point, this Castle, if a number of rational points is the maximum allowed by the Lewis bound here, and also the Weierstrass semigroup at this point is symmetric. That is 2 times g minus 1 is a gap. And well, Castle code is one-point code where we take the point q and d is the sum of all other rational points. What do we gain with codes coming from Castle curves? Well, like in the Hermitian case, we gain the ability to manipulate them, to calculate, we have many equivalences, and like this. The first property implies something like that. If we take a function with pole order at q p2, then we can see this function as a map to the projective line, but q goes to the infinity, and all the fibers are totally split. All fibers are totally split. So, and have the same number of points, of course, v2. So we have, again, we get a lot of equivalences of divisors, like in the Hermitian case. In particular, the divisor t is equivalent to n times q. And again, we can simplify the parameters, and again we can use many equivalences here to compute the minimum distance, to compute generalized Hamming weight, and so on. So, excuse me, the second property. About the second property, the 2 times g minus the semigroup is symmetric. This means that this divisor 2 times g minus 2 is canonical. So when we use the formula for for duality, for dual codes, well, we can substitute here, and we find that the code, the dual of 1-point code, is not 1 point, but it is isometric to 1 point. It's isometric. So using these curves and codes gives an advantage with this kind of elements play a role. But that's always. How difficult is to find Castle curves? Well, several curves are Castle: rational curves, hyperelliptic maximal curves, Hermitian generalization. There are a lot of generalization, in particular Nobtre, Suzuki, Ray, and said before, a study and manipulation of codes coming from these curves is generally simpler than codes coming from other curves. Several authors have investigated properties of Castle codes, and some of them are here in this meeting here. They could probably tell us more about these curves than I can. Recurve Castle has been proved by Fernando and by Saed Tafazzolian. A family of Castle curves related to Hermitian has been given by Rivelto Borges and Ricardo Corseisao, in several papers. in the same line also by Heriberto and Alonso Sepúlveda and Guilherme, yeah, and minimum distance and also generalized Hamming weights were studied by Wilson Olaya and Claudia Granados, and also particular cases of Castle curves or related to Castle curve have been studied. For example, the duals of trace code, Castle codes, have been studied by Eduardo Balico and Alberto Rabagnani, or codes over Kummer extensions by Alonso and Ariane Masuda and Luciane Kuos, and codes on curves defined over by equation on separate variables which are closed, also by Matteo Bonini, Giovanni Cini, and Maria Montanucci, and so on. But instead of speaking about the properties of more properties of Castle curve, I prefer to speak about a couple of applications to maybe to understand better. Well, Castle curves and codes have been used in some other related fields, of course, in AG codes, but also in quantum error correcting codes, locally recoverable codes, polar codes, and several. I would speak about two of them if I have the time. About quantum codes. Well, quantum codes are used to protect quantum information. The main difference maybe is that we use qubits instead of bits. A bit takes the state 1 or 0, and while a qubit is a superposition of states, it can be described as a linear combination of 0 and 1 with complex coefficient. So a quantum code is a subspace of a Hilbert space, a complex space, and a quantum stabilizer code is a q to the power k dimensional subspace of C to the power q to the power n. We denote this form with double brackets to see that it is a quantum code. It happens that most coding theorists don't know anything about quantum mechanics, and the construction of quantum codes is a kind of mystery for us. This is for my case, for instance. Fortunately, the situation improved with a technique introduced by Robert Calderman, Peter Short, and Andrew Steen in the year 1996. And this is called the CSS construction, that allows to construct quantum codes from classical codes. Well, this saves us. In two ways, we construct quantum codes from classical codes verifying a self-orthogonality property. Firstly, over a field FQ, if we have such linear code containing self-orthogonal, then we can derive quantum codes with these parameters. But also over FQ squared for self-orthogonal codes with respect to the Hermitian inner product. The Hermitian inner product is the translation to FQ squared of the usual the Hermitian product in the complex numbers. And well, it happens that this is difficult to handle. It's not clear when this condition of self-orthogonality holds or not. Of course, this is for general linear codes. We can try to apply AG codes, and it seems particularly good candidates because, well, we need self-orthogonality, and we have we can characterize self-orthogonality for AG codes. Hermitian self-orthogonality, we have not results for AG code, but it can be translated to the usual to usual dual code by raising to the qth power. The condition of self-orthogonality is equivalent to this expression, which is, again, is not easy to characterize, but for AG code is not difficult. So let's proceed with AG codes. 1 point AG codes, for which we have not only one code, one isolated code, but in general, given D and Q, we have a sequence, a chain of codes from 0 to the whole space. And we have several possibilities for orthogonality here. In general, this holds for general codes. Given a sequence of codes, like the previous one, starting from 0 and going to q to the power n to the whole space, we say that the sequence is self-dual when the dual of each code is another code in the chain. And this is too strong, usually. We say the sequence, the chain is isometry self-dual when the dual is not in the chain, but is isometric to a code in the chain. And the vector x is always the same for all codes in the chain. Maria gave us a talk about symmetry duality Tuesday, I think. Yes. The thing is that we can obtain quantum codes from sequences like this, from such a sequence. Remember, we had two possibilities for the usual inner product over FQ, for Hermitian inner product over FQ squared. When over FQ is just apply the result, we get a quantum code. For the over FQ squared, for the Hermitian product, just apply the trick we say before, and we can translate the Hermitian dual to the usual dual. If the sequence is self-dual, then we have a quantum code. If the sequence is not self-dual, but it is isometry self-dual, and there exists the square root of the vector x given isometry, we can multiply by this square root, and we get isometry dual sequence. So we get a quantum code, and finally a trick. If the sequence is isometry dual, but this square root doesn't belong to FQ, what can we do? Well, we can start from sequences over FQ, then the square root certainly exists over FQ squared, so we consider the sequence over FQ squared, and again we apply the result, and we always get a quantum code. This can be applied to any code, but it works particularly well for Castle code. We use a Castle code. We have this change of codes. We remove all repeated codes, and then we have an isometry dual sequence by the property of Castle codes. Then the conditions we need is to ensure, you remember, c to the power q should be contained in G dual, but this for algebraic geometry codes is simple. It's just multiply. This code is contained in this code, and always we get quantum codes for which we can give estimates for parameters. Symmetry dual codes have been studied by several authors, Maria Bras and Ivan Duzma, and Maria Bras, Alonso, and Luciani in the two-point case. And also, if you look in some detail, you know that we used mainly the condition, the two conditions for Gaussian curves. We use the second one, the one ensuring duality. So we can, the Castle condition can be weakened, and refinements of this condition have been studied by Fernando Hernando, Gary Maguire, Francisco Monserrata, and Julio Moyano, and later by Daniele Bartoli, Maria Montanucci, and Giovanni Cini, who define a new type of curves they call Swiss curves and Swiss codes. Okay, this is about quantum codes. The second application, we use the second Castle condition. About the first Castle condition, we can speak about another application. This is to locally recoverable codes. What is the problem here? The problem is distributed storage. I mean, the problem comes from the huge amount of information we manage in modern times. We store a big amount of information in, say, think about clouds or something like that. And to be efficient, this is done in a distributed form. This means that this is done over servers anywhere in the world. We have a long sequence of symbols to store. We cut the sequence into blocks of the same length, and each block is stored in a different node. The problem comes when a node fails. When a node fails, the information is lost, and we want to recover it. How to recover? This is the repair problem. Well, a trivial solution, but used in practice, is to replicate the same information on several nodes. But this is expensive. It's not clever. A better option is to use what is already invented, that is recording code. We can see each block as an element of a field Q is L to the power M. And we can use recording codes over this field Fq. We encode information we want to store, and we store the code word. So using the code, we can recover ratios. The problem, the drawback of this method is that when we want to recover a lost coordinate, a lost information in a node, lost coordinate, we need the whole information of the code where it belongs. That is a lot of servers. So it is natural to wonder if can we do it locally? I mean, using not all coordinates of the code word, but just a few coordinates around the ratio. This is local repair. For example, Red Solomon again. We want to store B1, BK. We take a Red Solomon code. We construct this polynomial using the information we want to store. We choose elements alpha and evaluate this alpha, and we store these evaluations. When a node fails, we can recover the polynomial just from k nodes, because it has degree k minus 1. So we need k nodes instead of n nodes. Formally, a coordinate is called locally recoverable if of locality R if there exists a set of other coordinates which uniquely determine coordinate I. these coordinates form a recovery set, and the code is locally recoverable if all coordinates are so. The problem is how to construct these locally recoverable codes. Is it difficult? Well, it is not, because every code is locally recoverable, and the locality is at most dimension, of course. But we want codes with a small recovery sets. So for Solomon, the previous transparency, it is used in fact in several systems. It is used by Google or Facebook or things like that, but it really is the worst option. Can we do better? Can we use algebraic geometry codes to solve this problem? Well, the idea is it comes from a couple of articles by Alexander Barr, Isaac Tamo, and Sergei Fladut, and this is as follows. We take a curve, we take two rational functions, phi1, phi2, and we consider phi1 as a map, again as a map from the function to the affine line or critical line. And we consider fibers with r plus 1 elements, many elements. And we construct an evaluation code from these ingredients. We need points and we need functions to be evaluated. Points are the union of fibers, and functions are of this type. Powers of phi1 times phi2 to the power I, which is at most r minus 1, and the evaluation code. What is the trick here? The trick is that a function in this space is well, has some powers of phi1, but phi1 is constant over the fibers, of course. So phi1, the function f acts as a polynomial on phi2 when we restrict to this fiber phi1. So since this is a polynomial of degree r minus 1, our data is enough to determine it and to recover the information. Well, more or less. So in this way, we get an LRC code, a locally recoverable code of locality R. And in fact, this method for the simplest case, for where the curve we take is the projective line and the functions are polynomials, is becoming the standard. But we can do it with any curve. Since the time is over, we just mention that what is the best choice for the curve and for the functions phi1, phi2? Well, the best choice again is when the curve is cancelled, because in this case all the fibers are totally split, and all have the same cardinality, which is V2, the multiplicity of the Weierstrass semigroup. And then the code is as large as possible because it has all the rational points in the curve. And I think that's all I want to tell you. Thank you for your attention and for your patience. And I don't know if you have a question or something like that. Thank you very much.